Questions about anything from last time or anything? Well, hopefully the technology will work today better than it did on Friday. On Friday, I showed you the Cauchy integral formula. And I told you right away we'd start harvesting some of the big applications of it. So remember, it's about an analytic function inside and on a simple closed contour, gamma. So that's a Jordan curve. It has an inside and an outside. And gamma needs to be counterclockwise. I maybe didn't emphasize that enough last time. And if A is a point inside the simple closed curve gamma, then the Cauchy integral formula says the value of f at A is this simple formula. And the mind-blowing thing is this shows that the value inside that curve only depends on the values of f on the curve. That's pretty unusual. It means that analytic functions are kind of rigid. You can't push them around. And last time I did it very carefully on the disk, but I could have done it on any curve to show you that that thing on the right can be differentiated with respect to A under the integral sign. And when I did that, I did it once and got f prime of A. Oops. I can't believe I dropped the I there. The person who taught me complex analysis kept forgetting to put the 2 pi i's in, and so at some point during the semester he said, from now on, assume that 2 pi I is equal to 1. And when you differentiate under the integral sign here, the first time you'll get a z minus a squared. I'm differentiating with respect to a. So that would be minus 1 over z minus a squared. But then since it's minus a, it makes it a plus 1. The next time a 2 would come out, the next time a 3 would come out, and the general formula is that the nth derivative at a is n factorial comes out. And the power in front of the power of that denominator thing is always 1 bigger than the number of derivatives you're taking. Simple induction shows that. Well, today I'm going to apply this and get something called the Cauchy estimates. And the Cauchy estimates are going to allow me to prove these big theorems I mentioned at the top of the lecture, namely Liouville theorem and the fundamental theorem of algebra. I would call this one of the highlights of the course, because those are definitely biggies. And they're a major reason why complex analysis is so important. So these are Cauchy's estimates, or I guess the Cauchy estimates is what I call them. And it's when you apply this formula in a special situation, namely on a disk. So I'd have f that's analytic on a slightly bigger open set containing a disk. And so that's going to be a circle of radius r about the point at A. So this is going to be a circle about the point A in the counterclockwise sense. And I'm going to apply the Cauchy estimates at that point, the center. Well, when I look at that formula, I guess I should write I'll write out what the estimates are. The estimates are the nth derivative at A, the center of the circle, is less than or equal to n factorial times the maximum value of the modulus of f divided by r to the n, where m is equal to the max of the modulus of f on the circle. That's kind of weird. That means you can't wiggle too much. If the function is nice and bounded on that circle, it can't wiggle too much on the inside. So things like wiggling sine things that wiggle really fast, that are bounded by 1, are doing things that are not allowed in complex analysis. That's the estimate. The proof is really simple. When you look at that, when you look at the integral formula, you get, let's see, the nth derivative at a is equal to the modulus of n factorial over 2 pi I integral around the circle. Here's the f of z in the numerator. That's where the m comes from. And here we have a z minus a to the n plus 1 dz. And let's see, the z is going around that circle. So here's the z in that integral. Z minus a is equal to r in modulus. So the modulus of z minus a is equal to r in this thing. And so when I do the basic estimate on this integral, I would get this is less than or equal to, I get an n factorial over 2 pi. I get the maximum of the modulus of f on the circle of radius r about a. And that thing in the denominator gives me a 1 over r to the n plus 1. And the basic estimate says now I have to multiply this by the length of the circle, which is 2 pi r. So that's the length of the circle of radius r about a. And note, and that's where one of those powers of r gets canceled by the 2 pi r, and the 2 pi goes away, cancels, and so sure enough this is less than or equal to n factorial times m divided by r to the nth power. So check. That's all there is to that. Okay, and the first big theorem that's going to pop right out from that is Liouville's theorem, which I stated last time. Bounded entire functions must be constant. Okay, so bounded just means that f of z is less than or equal to some bound. And entire functions means that f is analytic on C, the whole complex plane. And it's the proof is just the n equal 1 case. N equal 1 Cauchy estimate. That's all there's going to be to it. And so let's set the proof. We start with picking any point A in the complex plane. Pick any point A in the complex plane. And when you apply the Cauchy estimate, you realize I can take that bound M to be the bound on the whole stupid complex plane. So we assume f of z is less than or equal to m, or let's just make it less than m, that doesn't really matter, on C. And then the Cauchy estimate with n equal 1 tells us that f prime at A is less than or equal to 1 factorial times m divided by r to the 1. I'm putting a disk about A of radius r. And then when you realize, that m is the same thing no matter how big I take that circle. So the thing we notice here is I can let r go to infinity. Let it get arbitrarily big. So I can let r increase indefinitely. And we see that f prime of a must be 0. It can't be less than any positive number, so the only case is that it has to be 0. So we see that f prime of a was 0, but a was arbitrary, so that means that f prime is identically 0. That's all there is to it. So that means that f prime is identically 0 on C, and so f is constant. Complex constant on C. Okay. That's kind of cool. And it's so simple. And so now I'm going to show you that Liouville implies the fundamental theorem of algebra in a very straightforward manner. So next, Liouville implies the fundamental theorem of algebra. I guess before I do that, I need an estimate, which is going to be useful in a lot of things we do in the future. So I'm giving it a name. The book doesn't use this terminology, but since I'll refer to this thing quite a bit, I'm going to call it, when I had those basic estimates for integrals, I call this thing the basic polynomial estimate. It'll be very useful when we do residue integral calculations, which will be quite soon. So it applies to a polynomial with complex coefficients. Call these complex polynomials. A n z to the n plus etc. down to a1 times z plus a naught. And to be of degree n, we assume that the leading coefficient is not 0. If it were 0, we could just dump it and not write it. So it makes a lot of sense that it's not 0. And we assume that n is bigger than or equal to 1, so it's not a constant function. So all that means is that p is not constant. Then the basic polynomial estimate says there are real constants let's see, they're all going to be positive. So 0 less than a less than b, and a radius which is also positive, such that the basic polynomial estimate is az to the nth power is less than p of z in modulus is less than bz to the n when the radius is bigger than, when modulus of z is bigger than that radius, so outside some circle. And so that shows you that that polynomial for big Z modulus blows up just like modulus z to the nth power. So it's bigger than that constant times it, and it's less than a constant times that. So it's squeezed into that exact kind of growth behavior. It grows like mod z to the n. That's the word mathematicians would use. Think the modulus of p of z blows up or grows like mod z to the n as the modulus of z goes to infinity. And something to note, remark, note that all the zeros of the polynomial, they can't be outside that circle of radius r, because the polynomial is strictly, the modulus is strictly bigger than 0. So all the zeros, if any, all the zeros of P of z fall inside the disk of radius r, about 0. There's none outside that. Well, this basic estimate is pretty easy to demonstrate. So the proof of the polynomial estimate. Let's see. You just factor, when you write out the polynomial, you can factor out the z to the n. So you get z to the n. And when you factor out that, then the first coefficient thing would be an, just a constant. The next one would be an minus 1 over z. And et cetera, down to a1 over z to the n minus 1. And the last one, a naught over z to the n. Call this thing right here h of z. Why not? Notice that they all have z's in the denominator. So that h of z goes to 0 as z goes to infinity. Okay, and that's going to be the key. So let's see. Let's think about a picture here. Here's 0 in the complex plane. An is a complex number, and it's not 0. Okay, and h of z, let's see, I'm going to draw a picture like this here. Let's put a pretty small circle here of some radius. Why don't I call this radius rho? And I want this picture like I've drawn here. I want my h of z, so this spot right here is going to be an. Did I write a 0 there? That's weird. That's going to be an plus h of z. That's the thing inside the square brackets there. H of z is going to 0. So I want it to be inside that circle of radius r. And let's see. Now when I realize and look at that picture, I realize what my a and my b are going to be. If I draw a dotted line like this, this distance is my a. This distance right here is my a distance. And this distance, let's see, this distance is my b distance. So inside that circle of radius a, the point an plus hg is between the circle of radius a and the circle of radius b. So we see from the picture, we see that an plus h of z is between the circle of radius, the circle of radii, a and B, defined by the picture there, when h of z is less than that radius rho. Let's see, so we want h of z to be less than the radius rho, and we want the radius of rho to make that picture valid, we want that to be less than the modulus of an. And so the inequality follows. So what do we get when we look at that? We get that, did I write it correctly up here? Oh, yeah, I should have written p of z over z to the n there on the left. So when I do that and put it over there, I get p of z over z to the n. That's the point an plus h of z modulus. And now I see it's between a and b. When h of z is less than the rho. Which happens when z is some bit bigger than some radius. So that's all there is to that inequality. For some r. Since it goes to 0, the h of z goes to 0. Questions about that? Yeah, I'm going to use that again and again and later on, so that there's a word for this basic estimate. Let's see. And notice if I made that rho really tiny, which I could do. I could call it epsilon instead of rho. And then the a and the b would be really close together. So it's kind of a fun fact that the a and the b could be as close together as you want. Fun fact. By taking rho really small, we would get a less than the modulus of an less than b, and make them as close together as you want. A and b can be as close together and as close to an as you want. You just might have to make that r bigger. What's r? Oh, the radius. It's since h of z goes to 0 as modulus z goes to infinity, I can make it less than the rho when mod z is bigger than r. Some r.
So there's two radius here, rho and r.
Capital R is modulus is the radius for the modulus of z, and little rho is in that picture. I need h of z to be within a distance rho of an. Yeah, so there's two different radii with different meanings. Don't really need to use that fun fact, but it's nice to know that it's incredibly close to a polynomial looks like an z to the n, really, and is sort of indistinguishable from it for a great big z. I should say that some books tend to take, in fact, our book does the same thing. They take rho to be equal to the modulus of an over 2. Just so they don't have to talk about it so much. I don't mind talking about it. Okay, this is kind of a drum roll moment, because now I'm going to demonstrate the fundamental theorem of algebra. And that's going to demonstrate the utility of complex analysis. So one way to say it is that a complex polynomial of degree n bigger than or equal to 1 has a root. In the complex plane. Of course, a root, R is a root, means the polynomial at R is 0. I'll call that complex polynomial P, of course. And the proof, suppose it doesn't have a root. Suppose we have a P of degree n with no roots. Not have a root. Then, if I take 1 over P of Z, I get an entire function. 1 over P of Z is entire, and guess what? It's a bounded entire function. We have the basic polynomial estimate. Which is a z to the n less than P of Z to the n, is less than B z to the n when the modulus of Z is bigger than some radius. Okay, so I'm going to want to show that the 1 over P of Z is bounded entire. And let's see, so if I'm going to estimate 1 over P of Z, to get that less than something, I need the P of Z to be greater than something. And so the side of the basic polynomial estimate I need in this case is this side. So that's going to be less than 1 over A mod Z to the n when mod Z is bigger than R. Okay, I want. That's interesting. Well, I can assume that R is bigger than 1. I can take that R to be as big as I want. That way, mod Z to the n would be even smaller than R to the n, 1 over it. So I can take R bigger than 1 so that Z to the n is bigger than R to the n when mod Z is bigger than R. Okay. And so what I've gotten here from the basic polynomial estimate is I get that 1 over P of Z is less than 1 over A R to the n. That's just a number. When, I'll write it like this, when mod Z is bigger than the max of R and 1. Put this as a remark. I had to think about what if R was less than 1. That'd be kind of dumb. I'm thinking of R as something big. So does that make it a bounded entire function? Let's see, why?
It's bounded on the exterior of the circle.
Right, so what bounds it on the rest of the plane?
Maximum of it.
Yeah. And why does it have a maximum?
Continuous function on that.
Exactly, yeah. So, and, let's see, F analytic, not F, 1 over P of Z analytic implies it's continuous. And a continuous function let's see, that implies 1 over P of X is continuous, and that implies the modulus of that. If you take the modulus of a continuous function, you get a continuous function. So quite often, maybe I skip saying things like that, but they're important. So that implies that it's a continuous function, and a continuous function on a compact set, also known as a closed and bounded set in the complex plane. On a closed and bounded the word for that is compact set, like the disk of radius r about 0 closure. So that's the set of z such that mod z is less than or equal to r. Attains its maximum. Okay, so the bound, we get a bound. I'm kind of beating this to death, but it's good to do that once in a while. We get a bound for the 1 over P of Z, the entire function, given by the max of 1, R, and the max of P, 1 over P, on the disk of radius R about 0 closure. So now Liouville's would mean it's constant. Liouville's, and of course that's crazy. Implies 1 over P of Z is constant. Of course, that constant can't be 0 because 1 over P of Z is just a complex number. Pick one Z and you get a number. That constant can't be 0. Is not 0. And the reason you can see that is pick Z equals 0, for example, to see that. It's not 0. And that means that, so P of Z is constant. 1 over that constant. And that's crazy. Why is that crazy? So that's going to be a contradiction. Why is that crazy? Yeah.
Because we said before that n has to be greater than or equal to 1.
Before the n?
We set in the initial conditions.
Oh, the n. Yeah, so why can't a polynomial be a constant function? I can torture this class. I can make you sit here and sit. Yeah.
But constant polynomials have degree arguments.
It's true that a constant polynomial... yeah, that's true. The basic polynomial estimate would lead you to believe it couldn't be constant because it has to get bigger and bigger. That's one way. But maybe I won't torture you any longer, but why couldn't it be constant? The simplest reason to get me off of your back is to say that the nth derivative of P of z is n factorial times a n, which is not 0. Let's see. Let me do the capital nth derivative. The nth derivative of P of z is n factorial a n, and that's unequal to 0. So that there's no way it could be constant, because then that would be 0. Or you could use the basic polynomial estimate. To see that how it couldn't possibly be constant, because it's got to get arbitrarily big. By the way, the fact that 1 over z, P of z goes to 0 and infinity does imply that that constant has to be 0. So I could have also done that to get a contradiction. I get a constant which clearly can't be 0 by putting in z equals 0, and then I say, oh, but that constant is arbitrarily small because P goes to 0 at infinity. I mean, P gets big at infinity, so 1 over it goes to 0. Okay. Question?
Could you explain why the constant can't be 0?
Well, stick in I know it's constant. Stick in z equals 0. 1 over P of z is not 0 because I assume it didn't have a root.
Right.
So that's just a number. So that tells you what the constant is. It's kind of like your ODE class where you pick a point to figure out what your constant is.
Oh, yeah, you're right.
Yeah. Well, that's a fantastic thing. And it kind of shoves it in your face that complex analysis is important. And just to understand basic polynomials, you've got to go to complex numbers. So you just have to. And a corollary of the fundamental theorem of algebra is that polynomials can be factored over the complex numbers. By the way, there's a word for the fundamental theorem. If you have the fundamental theorem of algebra for a certain field, the field is called closed. That's a big word. So the complex numbers is a closed field and a complete topological space, metric space. Every Cauchy sequence has a limit. Those two things make it heaven. Let's see, so this corollary follows from the thing you learned in junior high school called the Euclidean algorithm. You know, you did it. You take your polynomial. You want to divide P of z into Q of z. You do that Euclidean algorithm, and you get a quotient. And then you're doing this routine of subtracting stuff, and at the very end, you get the remainder. So that's the degree. That's the remainder. And of course, in order to, let's see, the degree of this remainder is less than the degree of R, strictly less. A degree of P. And when you do that Euclidean algorithm, it gives you the quotient. Q is the quotient times P plus the remainder. Okay. Well, let's say we find a root. Say A is a root of P of Z. Then when I do the this Euclidean algorithm, let's see, I want it to be let's see, is a root of Q of Z. Then when I do the Euclidean algorithm, I'd have Z minus A going into Q of Z. I do the Euclidean algorithm, and when I get down to the last step, I got to get something that's less than degree 1. So that would have to be a constant. So that thing is a constant. Because the degree of the remainder has to be less than the degree of P, which is equal to 1 in this case. Degree of Z minus A, which is equal to 1. Okay, so what does that mean? That means that I'll get a quotient when I do this, Q of Z. This means that Q of Z is equal to Z minus A times my quotient plus B. But I assume that A was a root. And so when I plug in Z equal A, I get a big fat 0 is Q of A, and that's A minus A, which is also 0, times little q of A. Plus my B, and we see that B is equal to 0. That means Z minus A divides capital Q. So the fact if Q of A equals 0, Z minus A divides, that's the word for being a factor, divides Q of Z. So my fundamental theorem of algebra says it has a root. And so I can factor out 1. Then I get a polynomial. Q is of degree n minus 1. So note, the degree of Q, my degree of my quotient in this case, little q, is equal to the degree of capital Q minus 1. So I can repeat this process. The fundamental theorem of algebra gives me a root every time the degree is bigger than or equal to 1. So repeatedly use the fundamental theorem of algebra repeatedly and when you do that, you'll get that you get P of Z is Z minus the first root, I'll call it R1. That times a quotient, and I would do it again, I'd get Z minus another root. And I'd do it again, etc. ... The last time I could do it would be the nth time. Every time it goes down by a power. And then the very last time, it would go down, and then the degree would be 0. And so when the degree is 0, the quotient would be a constant. This is the last remainder. And if I plug in, let's see, how would I see what the z is? Well, I'd multiply it out, and you'd see that the z to the n coefficient would have to be b. So it's easy to see that b is an, just by multiplying that out and using induction. Okay, and it's okay if those roots repeat. So you can have repeated roots. So it's okay for some r's to repeat. And so the conclusion is you can factor, and I would get P of z is an times z minus 1 root to the multiplicity m1, z minus another root to the multiplicity m2, dot, dot, dot. The last one would be z minus some root, let's call it r sub l, to the multiplicity m sub l, where the sum of those degrees, multiplicities, is the degree of the polynomial. Okay, so to really understand a real, even if the polynomial had real coefficients, you have to do this complex factorization to really understand it, and especially understanding the roots and the possibilities that exist. And that's really the beginning of algebraic geometry, which is exciting. Yeah, you got to have complex numbers to do algebraic geometry correctly.
Is that a question on this? Shouldn't it be the last quotients instead of the last remainder up there?
Let's see.
That should be the last quotient instead of the remainder be 0.
Oh yeah, this is the last. The last quotient would be of degree less, and it would be a constant because we get down to degree 0 at some point. Thank you. Yeah, I was showing the remainders were always 0. So that was dumb. The last quotient, the degree of the Q would be equal to 0, and so it's a constant. Certainly can't be a 0 constant because the polynomial is not 0. That's a good place to stop. Any last minute questions about anything? Well, I call this a high point of the course, but it's not going to go downhill from here, that's for sure. Okay.
Yeah.
Sure.
I'm trying to integrate this here on this circle. Not going this
What
way,
is it?
going this way.